So it has started. Siddhi, you share the screen and then proceed.
Yes, sir. Good evening, everyone. Welcome to the Centenary Celebration of the Department of Mechanical Engineering, IIEST Shibpur. Today, we are here for the 23rd lecture series under this series, which is to be delivered by our honorable guest, Dr. Dheepa Srinivasan, on the topic Successful Qualification of Additive Manufacturing for the Aerospace or Gas Turbine Sector. This session will be hosted by Professor Devdul, will be chaired by Professor Devdul Das, who is Associate Professor and Head, Department of Metallurgy and Material Engineering, IIEST Shibpur. Over to you, sir.
Professor Devdul. Yes, Professor Das. Over to you.
Yeah, it should have been Professor Devdul Das. Sorry for the mistakes. Sir, please take over.
Yeah. Thank you, Siddhi, and hearty welcome to all the guests, alumni of our institute, and our honorable speaker. Special thanks to Dr. Paul and Professor Ghosh for organizing this. This is 23rd lecture, so things are going for a long time. There is a lot of effort going on to organize these things. Today we have an excellent lecture. It will be delivered by first, I think I have been told that this will be first women scientist in this plenary lecture, Dr. Dheepa Srinivasan. She is presently acting as a chief engineer at Pratt & Whitney Laboratory, a United Technology Corporation India Private Limited. They have a permanent lab at IISc Bangalore. As a chief engineer, obviously she is responsible for all academic industrial research. Dr. Srinivasan received her MSc in engineering and PhD, both from the Department of Metallurgy, IISc Bangalore, in 1996 and 1999, respectively. She has more than 22 years of experience in the area of gas turbine engineering, specifically focusing on the material. She has invented several new technology, has over 35 patents, mostly USA patents, and has developed many technology who are behind the running of now several gas turbine and steam engine. She is the pioneer in the area of metal 3D printing or additive manufacturing, has developed several applications for metal laser additive manufacturing as a unique technology for application in gas turbine component repair, component life extension. Professor Srinivasan was awarded a certificate of excellence by Ministry of Steel, Government of India for her pioneering effect in additive manufacturing in the year 2017. She was conferred the Women Engineer of the Year 2020 industry category by Indian National Academy of Engineers. And Dr. Srinivasan also involved in teaching in many IITs and NITs, specifically in Indian Institute of Technology, Hyderabad, Raipur, and Vellore Institute of Technology. I think I have seen that she has, although she is coming from a, representative from Industry Institute collaboration. So I hope the primary focus is for the patenting, but still have many more publications, including prestigious, publication in prestigious journal like Acta Materialia, Scripta. I think year 2020 also she has a publication in Scripta, then many publication in Material Science Engineering. And this year itself, 2020, she has published 2 review papers on additive manufacturing. So I welcome Dr. Srinivasan to start his presentation. I think it will be enriching for all of us, including students. So let me invite Dr. Srinivasan, please.
Thank you very much, Professor Das, for the kind words of introduction, and congratulations to the whole Shibpur Institute for the centenary year. Indeed, it's a pleasure and an honor like to thank Dr. Maji for introducing me to Dr. Ghosh, and very quickly for us to, come together. It's always a pleasure for me to be associated with this institute in some way or the other, because I've heard so much about it during my PhD days almost 25 years ago at IISc. So once again, thanks for having me over. As I said, I have been working, as Dr. Das mentioned, I've been working mainly in materials technologies for gas turbines ever since I left IISc. I was working for GE for about 18 years. That is where, the introduction to thermal spray coatings, all kinds of materials technologies, single crystal welding and joining, and so on and so forth. What I'll be sharing today is some of the recent work, and all of this is available as publications. So since we are working for a corporate industry, we don't have much leeway to share. But fortunately, as Dr. Das rightly mentioned, I've always held my links with the university all through ever since I finished at IISc. So by way of MTech students, and the student interns have really been both my left arm and right arm, and that is how I've been able to publish a little, not so much, but still the wealth of knowledge and the accelerated development. That is what I'm going to show you here in terms of the recent qualifications in gas turbine components. I mean, people think additive manufacturing, and I think Professor Sarkar was asking how is it in the country. So I really do want to mention upfront that with university collaboration, with students, with faculty members, and by making it in India, that is what I'm going to be sharing today in the area of applications in gas turbines. So before I start, one sec, let me just minimize the screen. Before I start, I think this is one of my favorite slides, and it's statutory to show how, together with combustion and with design and with all kinds of advanced technologies that have enabled this engineering marvel, here is a 7-decade panoramic view of how materials technologies have really enabled both military as well as commercial engines. In fact, as I congratulate on the 23rd lecture series that has been organized with the Mechanical Engineering Department, I think if I was there in person today, I would have flown from Bangalore to Shibpur in one of these Indigo airlines, which is powered by the geared turbofan. Truly an engineering marvel, really. And I remember my professors at IISc talking about this in the 101 courses. What is fascinating today is not, of course, we have evolved all this with single crystals, with thermal barrier coatings, to the extent that today we're talking of firing temperatures far exceeding the melting point of the metal itself. And that is only enabled because of thermal barrier coatings, which are able to, insulate to some extent the nickel-based superalloys or cobalt-based alloys, and the very high-end materials. Today we are talking of green engines. Many of you would have heard, especially people who are there, both within India as well as outside. We're talking of how you can make hybrid engines, electric engines, and so on, and hydrogen as a fuel. But as we march towards all of that, what I would like to highlight in the next slide is really the chronology in terms of the timeline out here. Though the slide is a really busy slide, what I want to show you is typical product development in this high-end, engineering, structural engineering product, which is, which has very, very far-reaching design constraints compared to those used even in space, even in nuclear, even in automotive, even in locomotive, whatever you call it. I think aero engines, both military and commercial, have far more design constraint, which means it is a constraint for all engineering disciplines, electrical, aero, computational fluid dynamics, propulsion, combustion, etc. What I want to show you is this timeline: 1960s, then 70s, then 80s, then 90s, and now we are in the 2000 and beyond. The fact that to qualify one product, it takes about a decade, and to qualify one part, one manufacturing technology, one design in this product, in each of these engines, there are 60 to 70,000 parts, as you know, is about $1 billion by either EASA or a federal aviation agency. So in some ways, we're very thankful because it keeps us all gainfully employed. If I work on one technology after 45 years, after a PhD, I can retire with the same technology. So it keeps me motivated, working on it, as at the same time, of course, gainfully employed, as I say. But then time has come now. We're all in such a fast pace. Look at us, I mean, the kind of things, I don't need to iterate that to this audience, eclectic audience out here. I think the important thing I want to show is how can we go into the dream of something like high-speed civilian transport? How can we go into accelerated product development for advanced technology? We're talking of, we're talking of spacecrafts, we're talking of colonizing Mars, we're talking of so many things. And that is where I think really where I find additive manufacturing to really be a powerful technique, especially considering that it is still, as we spoke just a little before we started the formally the meeting, it is a little bit of a hype right now. I'm going to definitely talk of the advantages, the pros more than the cons. But then every technology, every manufacturing technology, as you all know, has a form, fit, and function. So we can't chock-a-block replace one with the other. We have to take the good and the bad together and then use the right form, fit, and function for accelerated technology development. So if that is the case, what are we talking about? Most of the work that I have done, at least in the published that which is available in the open domain published literature, has been in the area of repair and refurbishment of very high-end hot section components. I don't know if you can see it, in the back of my office, there are some cross sections on the walls out here of engines. But just for the students who have joined in new, and for those of you who are absolutely new and would like to get into additive manufacturing, I would say, I mean, the sky is the limit in terms of research opportunities. For us in the industry, we have to get translational research going. So in the sense, we have a very hard timeline. And that is where I told you, partnering with universities, having MTech students has really been the name of the game. I will iterate it as I go along. But just to start with, the reason why it is so attractive in the space and aerospace sector, even compared to all the others, it is all pervasive now, but even compared to all the others, is simply because hotter and lighter are the two common buzzwords that we keep hearing reiterated time and again in the sense of the aerospace and space. Because not that it is not in the others. For example, in an industrial gas turbine, lighter is not such an important metric. Hotter is in terms of power generation gas turbines, but cost is a big issue there. Whereas in the aerospace and space sector, it is a low volume, relatively speaking. I mean, it's not like the die casting industry of the automotive, high pressure die casting or injection molding, where we're looking at 10,000, 20,000 parts per day. Here, we're not talking of that kind of volumes. So these are the 5 performance matrices with which we'll look at why metal 3D printing or additive manufacturing is really going to be a game changer. It's already is, given the previous 2 slides that I showed you, in terms of high-speed civilian transport, increased firing temperatures, etc., etc. One is, of course, lighter, so lightweight reduction, which goes hand in hand with respect to simplification of parts. I mean, for example, the entire aero engine, those of you in mechanical engineering working on topology optimization, I saw Professor Ansuresh gave a talk in the series, I think as a previous speaker, he would have spoken to you about topology optimization, how it's playing a huge role in design for additive manufacturing. We always knew in the mechanical engineering class, the DFM, design for manufacturing, where design will far outbeat the manufacturing challenges in terms of tolerance, in terms of surface finish, in terms of wall thickness and so on. In the case of additive manufacturing, the design really defines the imagination of the design, the manufacturer. So you can literally, designer is left behind because, hyping it a little bit, manufacturing can really produce, at least with some of the additive manufacturing techniques, any shape, any section thickness that you want. So simplification of parts is a big important thing in aero engines, because if you take a heat exchanger, and practically the entire engine is a heat exchanger, and then you know how difficult it is to make these complex shapes, radial heat exchangers, these thin section fins, you weld it, you braze it, and you heat treat it, the whole thing distorts. So simplification of parts is the name of the game. And because of both these, of course, you're going to have an improvement in the performance and so on and so forth, and durability. So the reason I show you this chart out here is, like with anything else, when we have something new make, let me take a single crystal here. I believe I have one of the blades in the souvenir. It just occurred to me I can show it to you since I'm sitting in my office. I don't know if you can see my video and pointing to the 3-inch single crystal blade. This is the heart of most of your aero engines, where the heat energy is converted into the mechanical energy. In the case of an aero engine, of course, that goes, into forming a thrust. In the commercial engines and military engines, you have an afterburner. And in the case of an industrial gas turbine, you're, of course, going to use it to generate electricity, either with a combined cycle steam turbine or with, both of these run a generator. So if I take something like single crystal blade, which I'm showing you here, the entire thing has to be a single crystal without grain boundaries. There's a new acceptance standards out here. But, because of the low clearance between the blade and the shroud, especially when it's rotating and the plane goes through a takeoff, cruise, climb, cruise, and then landing, then you can see, obviously, I'm going to lose some clearance out here because of the rub, because of the high temperatures and so on. So I'm going to lose a little bit of the tip. Now, I'm actually showing you a souvenir that I took back from me in my previous job. And you can see this welded tip out here. Now, it's very, very difficult to weld, as you all know, a single crystal, because any welding is a melting and solidification technique, and you're going to have equiax grains here. So then do I throw this when it comes back after a year for after service exposure? It's so expensive. Not only that, you can't get it for love or for money, in a short span of time. So that is why I'm showing you the second line here. We're always interested in hot section components, component life extension. And the criterion we use, any technology that we use for refurbishing the parts, for putting them back, always goes back into the new make as a lessons learned. So it is the best tool to actually to give the boundary conditions when designers use finite element modeling iteratively for the next product, the next version of the product 2.0, or even a completely new product. So that's what I'm showing here. And this is where at least I started off, like maybe 13, 14 years ago, additive manufacturing, long before it became a buzzword. And I started in 2008, use additive manufacturing as a unique manufacturing solution for gas turbine hot section components. And that's what I'm going to be showing you with a couple of examples. But before that, let me share with you some of the Pratt & Whitney advances. I'm sure you like to know, especially Professor Sarkar was asking how prominent it is in India and also in the world in the aerospace industry, because aerospace is one of the toughest, aerospace and medical, both related to human lives, of course, to qualify and certify. And so this gives you a quick bird's eye view. It's not updated. It's about 1.5 years old, but still, qualifying for the aerospace industry does take a long time. So you can see here with respect to the simplification of part, this is a hot section part designed for additive manufacturing has been employed. There is a 99% reduction in the part count, 2 times mission life at the maximum exhaust gas temperature, and then operability equal to baseline. So I'm just giving you some example. Look at this prototype, 27 days from concept to engine delivery. See, normally when you're looking at a new prototype, especially in a complex thing like an engine development, even in a turbocharger for a land-based, auxiliary power unit or or an automotive part, to make from the design to the whole part, even with small scale industries, it takes a long time. Here with additive manufacturing, really, that is the name of the game. We are able to make prototype for testing, rig testing in a very short span of time. We're also able to come up with new engine designs, again, lightweighter, hollow blades, blade with discs, and so on and so forth. So this is some of the recent developments in Pratt & Whitney. And if you take the entire, we are now Raytheon Technologies, which includes both the engine, which is Pratt & Whitney, and then everything in an aircraft other than the engine, which is called Collins Aerospace. And also now more recently in the last 1.5 years, Raytheon Technologies, which is sort of the world's defense, land-based and other defense, is also joined. So there's a lot of parts, more than 3,000 parts have been qualified for various applications, rotating parts, stationary parts, for rigs, for building the prototype and actually going into the engine, just to show you a bird's eye view of the kind of progress that has gone on in this industry. So now if I really come to some of the case studies that I'm going to share with you, in fact, most of the work that I'm citing will be from this review article that I wrote about a year ago, and the challenges in qualifying additive manufacturing for gas turbine parts. And most of if you look at the market in terms of when we talk of metal additive manufacturing, automatically the mind immediately goes to laser powder bed fusion, simply because the footprint is about 300 or 400 millimeters by 400 millimeters. We do have larger machines, but the more popular ones are 400 by 400. And then next in line comes direct metal deposition, which is a laser direct energy deposition by using a coaxial lasers. And then you have many others, and ASTM is still deciding whether to categorize cold spray as a metal additive manufacturing, because the definition of metal additive manufacturing or even additive manufacturing is to take inputs, take a CAD model, slice the model into several layers the thickness of a strand of hair, and then give it to the machine into a G code, and then the machine simply draws out layer by layer process. So it has to get computer, inputs have to be from computer design. Now, so cladding, for example, even if it is a layer by layer process, many other things like metal injection molding are still not coming into the strict realm of the definition of additive manufacturing. So this rough chart, this traffic light signal is just to give you an indicator of, in terms of the part precision, the footprint, and the high throughput to start with, either by research or with, in any aspect when we start with to develop or work on aspects of additive manufacturing, it is good to have a rough idea on the form, fit, and function of where to start with, so that research or the product development is more meaningful. Of course, this is very well, a lot of review articles are there, so I won't spend much time on it. But I'll go on to tell you the areas where I have done a lot of work myself are in laser powder bed fusion, direct metal deposition, and cold spray coatings, which is not really additive, but it's a cousin of thermal spray coating. So these, we have qualified a lot of parts, both for the oil and gas industry as well as the aerospace industry, in between briefly for the medical healthcare population, in orthopedic joints, and also in the automotive and tool and die industry. So that's really where I go into the next slide, just to show you the alloys that I personally worked on. That is the middle where I'm showing the pointer. These are some of the aerospace and other qualified parts, automotive cast, conformal cooling tool and die, where it's very, very powerful. It's a stationary, because typical tooling, we are not able to get accessibility to manufacture the kind of cooling channels for heat extraction in the injection molding and high pressure die casting, where additive manufacturing is really very, very powerful. We are able to get section thicknesses very, very small manufactured, which is not possible in conventional forging or machining. And then a few other examples I'm showing you. And some of the new alloys that we are working with in the last couple of years in the Pratt & Whitney R&D Center, again, partnering with a number of universities, is listed out here. I'll come to that towards the end of the slide. What I'm going to share with you in the next 10 slides is really how we started from the conceptual level. Conceptual level means I'm not saying really at the, at TRL 0 where we have developed the new alloy. No, we have used some of the commercially available powders or wires, but taken it from starting from, coupon level. That's what I'm saying, by making coupons, by making test pieces, and then establishing the feasibility. By feasibility, where I not just mean bulk coupons, but actually doing the prototype with the section thicknesses, taking it to a TRL level 4, technology readiness level 4. That means we are presenting it as a possible outcome by testing all the mechanical properties, microstructure, reproducibility, repeatability, etc. And then taking it into a design change. That means from a conceptual level design to a detailed design, changing it in the bill of manufacturing from a conventional manufacturing to an additive. And then, of course, maturation, what I mean is to productionize it in multiple manufacturing techniques. So I'll just take you through this in some of them. And mostly what I'm going to highlight is really the successful qualification. Nothing comes without challenge, as all of you know, especially in a high-end technology for a very, very high temperature applications. So I will particularly showcase how we overcame some of these challenges. And just to impress upon you all, yes, challenges are there in any technology, any product, any qualifications, and how we can do it in an accelerated manner by collaboration. I think that's what I want to bring: industry, academia, and research lab collaboration in the right way, at the same time protecting the IP, at the same time ensuring students can publish, faculty members can publish, everything can be done if we set our minds together. So I will really emphasize this in the context of this particular centenary lecture series. So this is an example. All these are some of the published work. As I said, the only reason we are able to publish, even because of the collaboration with the universities. So this is the starting example. This is a power from an industrial gas turbine. It's made of a very complex cobalt-based superalloy called FSX414. It's a cobalt tungsten alloy. And after exposure in the engine, you can see very complex cooling channel. There are radial cooling holes out here that you can see on top of this coupon. There are divergent, very, very complex design. And, this comes back like a moth-eaten leaf after engine exposure. Really, some of you might have heard me talk about this, but really this is the first product that we qualified from India, got everything done from India. It is running all over the world now since 2017. So it's really very close to my heart. Also, because we were able to publish a lot, I'm able to show this case study. But I'll try to bring in a different flavor, as I told you before, to tell you how we were able to overcome some of the challenges even way back 6-7 years ago. If time permits, I'll show you the other example, which is through direct energy deposition. This is a meter-long combustion product. It is a stationary, very, very critical component of the combustion chamber, wherein the fuel and the air mix. And this is primarily responsible, a very small part, which is, the size of my little, this particular index finger. It's less than about an inch. But what is so fascinating about this part is it's critical for the fuel-air mixture. There is fuel, air, and water, which is there in the small teeth that you can call here. And this teeth would get worn out by vibrations in the combustion chamber. And there was no solution available. And this entire stainless steel tube with this very complex multi-material annular ring, along with a small, as I told you, lean mixture reduction gadget, would be worn out, and the whole thing had to be thrown out. There was no solution available because practically, if you see the cross section here, this complete section thickness, it is completely hollow. So again, we developed this in 2016-17, and I think we were able to save a lot of productivity savings and early turnaround time for the gas turbine engine. So I'll start with both these case studies. As you all know, of course, all of you know this, but I think one of the things I'd like to point out here is to start with not only to know which additive manufacturing technique to use, but to also ensure isotropy of properties if it is needed. Sometimes you don't need isotropy of properties. Sometimes you need directionally solidified for better strain tolerance, especially in an aero engine. The blade that I showed you a little while ago, you need a strain tolerance, very good strain tolerance along one direction, and you need isotropic behavior on the other orientation, transverse orientation. How is it possible? How do you manufacture such things with conventional manufacturing? So this cartoon that we just displayed is a layer by layer structure. This is a substrate on which you build it, and you can see the layer thickness not marked here, but if you look at the micron marker in the etched three-dimensional metallurgical microstructure, it shows you that there is isotropy both along the build direction and transfers to the build direction, which was really needed in this particular application in the power nozzle, as I showed you. And what you can see here in this optical microscope, which was taken by one of the students who worked at that time, is very, very fine-grained, weld bead structures. Sometimes you can see it, sometimes you can't see it. Not all alloys will display this weld bead structure when you etch the microstructure. But what is really important is a very fine dendritic structure that you see. So I won't go into the details of this, but I'm going to summarize 4 challenges or 5 challenges really upfront that you should look out for in every additive manufacturing, metal additive manufacturing that you're planning to use. Even if you're doing modeling, a lot of people are doing integrated computational materials. But I think right now, experimental validation of those is not completely robust. So you need a little bit of, you need to do both alongside to accelerate this whole development process. So very first challenge that we faced, 5-6 years ago was to get, not to get a dense structure that is such as what I'm showing you in the middle and the bottommost picture on the left-hand side. But the very first challenge today, not then, you can see that we got lack of fusion, we got gas porosity, etc. But today, what is the challenge? I'm trying to show you something quite different. Despite doing a design of experiments, the challenge we are facing is the less sensitivity in terms of the design of experiments, telling you which energy density you can choose from. For example, we get at least 5 or 6 energy densities, laser power, scan speed, layer thickness, etc., giving the same dense microstructure, at least at the optical level, which means going forward in terms of making the part to the section thicknesses that is needed, or variable section thicknesses in terms of mimicking let's say, this aero engine blade. For example, if I show you here, this is the leading edge is thicker, the trailing edge is very thin. And then if you look at this whole cross section, it's completely hollow out here. And then if I look at this section thickness, it's completely thick, several millimeters or probably half an inch thick. So how do I make sure the heat transfer is actually reproduced via additive manufacturing as I build this part layer by layer in order to ensure that the parameters that I choose in a bulk part, which gives me a dense energy density to result in a dense microstructure, how are we able to resolve between different energy densities or laser parameters, that all of which give you a dense part. So I'm really trying to show you 5 years later or 4 years later, the challenge that we face right now, which is why we say we always partner with integrated computational materials engineering to predict and to validate together. So that is challenge number one. Getting a less porous or a dense structure in most structural engineering materials in the periodic table today is a no-brainer, because people like ANSYS, Abacus, all these people, Magix, all these people have developed superior softwares that when you take from a CAD model to actually print this, is able to give you iteratively a very dense as printed microstructure. Okay. The challenge now is also to see how, as a function of build orientation, we are able to get a uniform, dense microstructure reproduced. The next challenge that I'm talking about here, which we overcame, is to go from an as printed structure. In case, of course, most hot section parts, most high-end materials, including steels, nickel-based superalloys, of course, titanium-based alloys, which are the workhorse alloys for aerospace compressor and so on applications, we need to heat treat. And moreover, when we are joining conventional with additive, as I showed you in this particular case study, actually I forgot to mention. So what we decided to do in this application is to cut out this, this damaged part, both here as well as here, and to use, in this particular case, 3D print coupons with that required geometry, and then join here with the cast part with a manual TIG welding. So in both these cases, I've given you the extremes. One is a conventional manufacturing, the other is an additive manufacturing, either via laser powder bed fusion or direct energy deposition. But the joining technique is going to be a conventional welding or brazing. So we have the extremes right in the first case study that I'm showing you, that was captured in terms of a hybrid manufacturing technology, and use the true potential of additive manufacturing, as I told you, in repair applications. So when I'm coming to that, then naturally any welding or joining technique needs to have a stress relieving. In any case, this additive manufacturing, you need to stress relieve, because you saw in the previous cartoon, it's a layer by layer process of melting and solidification. Now, if you remember, conventionally, until 10 years ago, 15 years ago, even today, when we do one weld join, ASME has several sections. ASME section 9 has so many protocols in terms of what all to do, because any weld joint is going to have a tensile stress across the boundary typically because of the nature of, melting near the boundary and shrinkage after that. So we need to do a stress relieving. So what I'm trying to point out in the second challenge here is can be a boon and a bane, but it needs to be watched out. That means we can use a rapid solidification of additive manufacturing. It's actually a panacea for all the people in metallurgy there. And really, I'm very happy here because this is one particular technology where metallurgists will be employed in full swing. Not even so much mechanical engineers or others, but you do need high-end metallurgical, very strong skills in metallurgy because it's rapid solidification, welding and joining, you get metastable phases. It's the whole thing that really needs an expert metallurgical knowledge out here. So what I'm showing in the second challenge is when we heat treated it, we got a complete recrystallized microstructure. And what we also did in the heat treatment optimization, if you can see this thin line out here, you have the potential to optimize the heat treatment to tailor the mechanical properties to have an advantage or a disadvantage here. So that's what we did. We converted this as printed structure with little or no defects. Of course, you see some micro cracks, you can see some porosity, but which casting or which forging doesn't have it. So we converted into this is an EBSD pattern which shows no orientation dependence as demanded by this application in the power nozzle, which was going to operate at high temperatures. And we also had a recrystallized microstructure, which is fine grained. Now, when our chief engineer saw this, they said, absolutely a no-no, Deepa, because you're going from a casting microstructure with large grain size, and you're going to have a 30 to 40 micron is the grain size out here. Absolutely no for this high temperature application, because fine grained microstructure is very bad for creep. So what I'm pointing out to you is a challenge number 2 of how you need to intelligently overcome this. And remember, all these were done in tandem in less than 1 year's time frame. So you go and look at evaluate the mechanical properties. Again, it's a very busy slide, but the fact I'm trying to show you here in item number 3 is 3 or 4 points. One is to look at the anisotropy of mechanical properties. Yes, additive manufacturing, by the fact that it is a layered structure, you tend to build an isotropic structure, whether you like it or not. Isotropy in terms of vertical transverse at 45 degrees in terms of mechanical properties, not like a forged structure. Maybe akin to a rolled, where you do see anisotropy, texture, and mechanical properties. So that you need to watch out. But you need to watch out that not at room temperature if the application is at high temperature. So we straight away went out and, of course, we developed all the room temperature strengths. That is a no-brainer. That has to be done as a statutory thing. But we straight away went and compared the high temperature mechanical strength. In terms of the baseline, a lot of people ask, do you have a baseline? Is ASTM having a standard for additive manufacturing? Remember, you don't need to have the standard, because when we are trying to develop a new part or a new product or a new alloy for additive manufacturing, we do have a baseline in what we are comparing it with respect to the equivalent cast or wrought part. And that is what we did in the slide. And we evaluated the creep, the low cycle fatigue, high cycle fatigue, thermomechanical fatigue. Since it's a high temperature part with the thermal barrier coating, we added a thermal barrier coating. So what I'm summarizing you to challenge number 3, it's definitely a challenge. You need to pay some attention to it. Not only in this property of uniaxial tensile or compression or creep, but also to pay attention to whatever the property demands. Let's say if it is a wear application, like I showed you in the DED example where there was a wear, we went and did a fretting wear. So you don't need to reinvent the wheel, and especially now in 2022, where there's tons of literature available, a lot of people in the world are working on different groups. So given the proprietary nature, sign a non-disclosure agreement and get, you don't really need to reinvent all the testing, because chances are it is available somewhere. You just need to do the reproducibility, because additive is fraught with build-to-build variability. So you need to establish that in challenge number 3 in terms of orientation dependent mechanical properties, and then you make use of the best out of it. And that's what we did in this application. And then next comes another, actually this is 3 and 4. I have combined multiple things in this slide, and then go into what is a big challenge in additive manufacturing. You might have all heard about it, is definitely surface roughness. Because in a conventional casting or a forging, we do have allowance that we give for machining. Build to print does have machining allowance, does have allowance is not only in the surface but in the fine cooling features as well, in investment casting and in forging. Whereas here, if I'm going to build the near net shape part, this entire turbine blade, then I don't have any machining allowance out here. I even with the expect to with respect to the external surface, I can give a small print and I can machine it. But what about the internal cooling holes? If I'm making a near net shape part, both here and here, it's very difficult. So this is definitely a big challenge to watch out for, because you can't machine such structures afterwards, especially after claiming that you're using additive manufacturing for making near net shape product with little or no post processing. So that is what we did in this example I showed you of the power nozzle, which is a hot gas bath component operating at temperatures over 900 degrees centigrade. So we try to optimize the laser parameters for minimum. If you look at the top part here, the surface roughness, you can see from a roughness of 15 to 20 micrometer RA, we brought it down to 3 to 4. At least on the external surface, it's okay. You can give some grid blasting. You can do some machining. What about the fine cooling holes, 0.2, 0.3 millimeter, 300 microns? How can I possibly know which cooling holes has a roughness like this? If you can see here, unmelted particle out here, a lack of fusion out here, and that will become a KT factor, stress concentration factor. Very, very difficult. So what we did is we partnered with our colleagues in aerospace here. We made a small CFD calculation to look at what is going to be the pressure drop if there is going to be a constricted cooling hole. What is going to be, because a pressure drop in a gas turbine component means I'm going to have the temperatures increase. It is going to give me a hot section. Excuse me. It's going to give me a hot section there, and that's a no, because that may even melt the material, that may decrease the mechanical properties if the temperatures go high so much, and so on and so forth. So what we did very cleverly in this particular example, and it can't be generic across all designs, all products, all cooling hole dimensions. In this particular example, we quickly changed the additive manufacturing diameter of the coal slightly larger in that particular customer product, and we calculated what is the pressure drop across that particular diameter. And the beauty of additive manufacturing is overnight you can change the design and 3D print it without having to go to a casting, a pattern, and then having the pattern qualified and then making a part of that's why this is so beautiful and it's so fast. So that's what we did, but definitely it's a challenge to watch out for, especially if you're working on actual product development. Now, the other important aspect I wanted to show you, despite all the hype and despite all the publications that have come out from various universities, I want to show you a very interesting thing that we did earlier this year. Inconel 718. During the COVID years alone, 2020, 2021, we looked at a review article that came out in early part of this year in February 2022. Inconel 718 is a workhorse alloy in the cast and the rod form. It's been used in the aero engines up to temperatures of 650 degrees, at least for the last 50 to 60 years. And it is one of the most 625 and 718 most well-studied alloys in the additive manufacturing community, both by electron beam melting, laser powder bed fusion, direct energy deposition, wire arc additive manufacturing, everything put together in the last 10, 12 years. But can you guess how many publications that came out, peer-reviewed publications, just in the last 2 years? Obviously, because people were locked in, and couldn't do. There were about 240 publications in good peer-reviewed journals. But yet, the number of qualified parts and rotating parts in the aerospace industry, if you count, hardly 1 or 2. And why is that? And they were at very low temperature or ambient temperature applications, because despite all this hype, what I'm saying is, despite all these that I'm talking about in terms of qualifications, what holds for one temperature may not hold good for the higher temperature. So even though I showed you 3,000 parts have been qualified with Pratt & Whitney, out of which maybe at least 10 to 20 products have been with IN 718 in terms of, gas turbine bolts, nuts, struts, manifolds, stationary parts, They still haven't gone to high temperature rotating parts like a turbine blade that I spoke to you about, compressor blade, because it still lacks high temperature knot sensitivity or ductility. So without going to the details of this slide, I wanted to still show you that there are still challenges, lots and lots of research opportunities for university to help us with in terms of fundamental science and understanding is, I won't go into the details of this, but I just wanted to show you how very recently we were able to partner with IISc here and then try to solve this problem of high temperature knot sensitivity and hopefully design a heat treatment and overcome this knot sensitivity out here. And then, if you look at the high temperature, what the additive shows in terms of the creep rupture at 690 megapascal and 650 degrees centigrade, it lasts only for 1.5 hours. Whereas the equivalent rod product is lasting for more than 50 hours, an order of magnitude higher knot sensitivity. So we solved this with very, very high-end advanced characterization techniques. This is an atom probe chromography. Not sure if the video is going to work. So we compared these two with two different heat treatments. I think this works. I won't go into the details, but I wanted to show the students especially what kind of things that you can help us with in terms of, most of the universities are, especially a university like yours and IITs and NITs are equipped with very high-end advanced characterization techniques. So we used atom probe chromography to actually decipher what was the root cause. And we were able to propose a heat treatment where we were able to overcome and propose to Pratt & Whitney a much superior, knot sensitivity on par with the rotor loss. So additive still has those challenges. That's what I wanted to show. I will move on here and skip this slide because I've already showed you the conclusions. And then I'll come to the 7th challenge. Remember, we finished up with surface roughness. What is a big challenge that is facing additive manufacturing? Taking the same case study which we qualified on the additive. This is a cast alloy. This is an additive alloy. This is cobalt tungsten FSX 414. This is cobalt chrome moly dissimilar materials joining. One of the big challenges that we are looking to with researchers is how do we quantify small scale mechanical testing? Because typically we test bulk materials. This is the ASTM standard specimen, ASTM E8 or whatever. What is a big challenge in additive is we are making near net shape part. So I can maybe get a small 2 millimeter mechanical test specimen, without damaging the part, take it out. But 2 millimeter or 1 millimeter, we don't have any acceptable test standards, isn't it? So what we did even 6-7 years ago in this case study is to weld this joint. I told you by manual TIG welding. We took specimens less than 20 millimeters across this weld joint because this was about 3 inch by 4 inch. I was able to even extract this thin specimen. The thickness of the specimen is less than 0.2 millimeters, 200 micrometers. That means I need to establish the microstructure and validate it with a standard ASTM bulk specimen. This is almost 2 inches long, this threaded specimen, and take take a mechanical testing specimen across this tie line and prove in this particular case, you can see that there was no debit to the mechanical strength across the welded joint. This represents the additive part. This represents a casting part, and the casting at temperature in the uniaxial testing across the weld joint of additive with casting was weaker. So when I proved this, I had to go through the whole thing of establishing additive as a standard ASTM test geometries, small scale mechanical testing. And now this is a big challenge. This is definitely the world is going. ASTM is also looking for proposals to fund research projects to fund in terms of high throughput, small scale mechanical testing, both for creep, for uniaxial, high temperature, etc. And this is a recent collaboration with IISc that I wanted to share with you. My collaborators are Professor Vikram Jairam and Kumar at the metallurgy department. We had a postdoc working on it. So what we are doing is we are doing creep testing. In fact, they have been working on it in this Pratt & Whitney project, funded project for the last 4 years. And we have successfully developed creep and bending, not in uniaxial tensing. And this entire beam cantilever is not more than 2 millimeters. few millimeters long and 2 millimeters wide. So we use digital image correlation in this example. You can see that with this bending, we are able to get on the right-hand side multiple creep curves using one particular beam. And I won't have time to go through this, but will definitely be share some of the published work. I'm sure they will also be able to happy to share several, at least 20 papers they have published in leading journals on establishing this is commercial pure lead, commercial pure aluminum, and now they're working in the last 4-5 years in engineering alloys directly for the gas turbine application. So earlier we used to, creep, we have Larsen Miller parameter, Momquin Grant, and they're large specimens. You need many creep frames, one stress, one temperature, reproducibility, repeatability. Here with one bending cantilever beam that is so small in dimension, 2 millimeters, you can even go up to microns, 500 microns. We are able to get across this cross section multiple creep curves. That is what I'm showing you here. And as a function of bending moment, you can generate the entire stress exponent, etc., and find the mechanism of creep in this, and use this both as a quality control tool in the build plate, location specific, as well as be able to do as a function of section thickness at various temperatures. So we are working on this and recently published a couple of papers on this. And this particular example that I'm sharing with you is how we are able to delineate between transverse versus longitudinal build orientation. Remember, I told you that is a big challenge in additive manufacturing because of residual stresses, because the nature in which layer by layer it is printing. So this is a particular paper that we shared in ICAM 3D and show how bending, high throughput bending can be able to distinguish between microstructural differences in a very quick manner using one bending creep specimen. And of course, that's what I'm sharing with you here, the creep analysis. High throughput data acquisition from a single creep test. You can see the load. They have facilities up to about 800 degrees C now in this bending creep. And how you can see on the right hand side, digital imaging correlation coupled with additive manufacturing is a very, very powerful tool for mechanical testing. And the beauty of this, I won't go into the details, but the beauty of this technique is you get tension compression data from a single bending creep specimen. No need to do compression test, tensile test. So for those materials with tension compression asymmetry also, we're able to decipher this. I will move on. I believe I'm close to the end of my talk, but another 5 minutes can I take? It'll be 7:30. And then leave the, can I take another 5 minutes?
Yeah, sure.
Okay. So we did, some, again, very, very strong collaboration with academia. We were able to do some of the mechanisms, what is responsible for creep in this. And then I'll come to the last couple of slides here. I want to leave you with 10 challenges. There are many challenges, but I'll stop with 10. What is the 8th challenge? The 8th challenge is in how do we optimize bulk properties, which is what we evaluate routinely, especially as part of a master's thesis or a PhD thesis, even when we are doing design for additive manufacturing. This is an example from a cranial implant. In between, I worked quite a bit with medical doctors to actually take metal additive manufacturing for patient population. So this is some hapless persons. We translated the DICOM image from a CT scan of a patient, of a person who had an injury, a brain surgery had to be taken place. And this is a cap that had to be put after the surgery. And then we wanted to do very quickly overnight. The doctor said I needed a cap made out of Ti-64. And then where do we run for vacuum heat treatment? So we had to look for thin wall section. So what I'm showing you on the right-hand side is genuinely a challenge in terms of how do we extrapolate not just mechanical properties, but microstructure from a bulk specimen? We normally print 1/2 inch by 1 inch or 1/2 inch, at least 3-4 millimeters thick specimens, isn't it? How do I go from there to a very thin section thickness is about 600 microns out here? How do we accommodate for the heat treatment, especially in quixotic materials like titanium alloys? where they're very, very sensitive to the heat treatment given, both from mechanical properties and microstructure. So that is a big challenge you need to watch out for. Material specific challenge also with respect to mechanical properties. And what is the challenge number 9 that I'm talking to you? All the mechanical designers will be able to empathize. When I'm 3D printing a bulk cube that I'm showing here, I get little or no porosity. I started with this as a first challenge. Especially we can optimize parameters to give little or no porosity. You can see these, this image analysis shows you hardly any 99.9% dense. Whereas if I take the same thing and I 3D print this particular blade out here, I'm showing you the cross section of a hollowed turbine blade, such as what I'm holding in my hand. And if the CAD model, by chance, there is 1 or 2 lines, just one line missing in the G code, look at what it results in. And this is a practical example that we faced recently that I'm sharing with you. One code missing results in complete, one entire line missing in this particular blade geometry. And what does that mean? I mean, that is disastrous. How am I going to even inspect that? You know, we don't have inspection technologies. And moreover, you can see a lot of unmelted particles out here. And I already mentioned to you before, in going from bulk to thin sections, completely different porosity. Here I can see at almost about 3% porosity. Here I'm seeing only 0 porosity. So which means this is a big challenge again to think of and overcome. And I come to the last challenge that I'm going to share with you today, which is bordering on where I left from the previous slide, namely how inspection technologies, huge research area. You know, what I'm showing you in the previous, the videos that you can see here. This is, we do have thermal monitoring. We do have photodiodes and thermal imaging that is possible in the build plate that I'm showing on the right-hand side, from the recoater side to the build side, across the build plate, especially if you're building many parts after the qualification. The top picture is able to show you, you know, splats out here, which means there is a warning out there that it's not a uniform build. The bottom picture is showing you something without keyhole, without lack of fusion. So there is a huge need for building inspection technologies. It doesn't exist now, even with the micro CT, especially in situ imaging. So I'll leave you with that challenge. And, you know, I'm just going to reiterate and close my talk by thanking you for the opportunity actually to share this. Once again, congratulate all of you. And this is some of the ongoing work in new alloy development together with lots of universities. I, again, will that and tell you that I've barely shown you, but I have shown you challenges that came from successful qualifications of aero engine parts and gas turbine components. Far more challenges. The challenges are only there to give us a learning opportunity. So I'm saying, despite all these challenges, specific to the application, we were able to overcome. But I just highlighted the 10 main challenges to say, as we enter a roadblock, we found a way to overcome these and yet was able to successfully qualify and put these, and there many thousands of parts have been made right from India, right from Bangalore, and additive manufacturing. We are able to take it forward from our country. So once again, thanks for this opportunity, and Centenary.
Yeah, many thanks, Dr. Srinivasan, for your nice lecture. I think it's clear to all of us that whenever we are producing, using additive manufacturing to produce near about onion net shape or even final product, then there is a lot of challenge to quality control, to quantification of the data, lack of standard is there, and also related to heat treatment, change of the microstructure, retaining anisotropy. So many thanks for your nice lecture. Now it is open. Or I think anybody can have, if you have any question or any clarification required, you can directly ask Dr. Srinivasan. Dr. Paul, if somebody is talking about, ensure that is unmute.
Yes, I think Dr. Das, can you please unmute everyone?
Yes, I have been given access to unmute them.
Yes, so anyone having any question, please can directly ask.
Let me congratulate Deepaji. First thing, my comment is really directed to the students. Let me be very candid. I have rarely heard this type of lecture where the speaker seamlessly go from one discipline to another discipline and identify the issues, challenges, and opportunities. From mechanical to metallurgy, from macro to microstructure, from interdisciplinary approach, identifying issues, I rarely saw anything. Thank you, Deepaji. I sincerely,
Thank you, sir. Thank you.
it's an excellent thing. What the takeout I'm talking to the students now is that this is an opportunity that you can think of just being a mechanical engineer is not enough. You have to be a metallurgist, and metallurgists are not enough unless you understand the mechanical aspects of it. It's not enough to understand the macrostructures design. You have to understand the microstructures. I do know many of you undergraduate students do not have the complete breadth of knowledge to appreciate what she said. But the take home is very simple. Take home message is very simple. Whatever you do, do it with a passion. If you are to understand something, just think a simple question. So if you are taking a standard, mechanical engineers, everybody knows it. Okay, there are ASTM standard, ASM standard. You can take a simple testing of tension, compression, bending, creep, easy. But now the question comes, can you do the scale it down in a macro scale? Obviously, there is no standard. That is what we are talking about. And that is what she emphasized it. And that really comes to one thing, Professor Devdulal, I'll tell you, it is absolutely important that we have working SAM. Unless we have a working SAM, we cannot say anything. She's talking about 1 micron scale. Our hair is 150 micron scale. We cannot say anything less than 10 micron. So it is absolutely important that we understand this thing. We have tools. Without tools, you cannot do anything. So it is important for the students and the faculty. The other thing I want to say is that thank you, Deepaji, for one more thing. You opened an opportunity for the faculty member to collaborate. There are a lot of things industry cannot do it. You identify them rightly.
Absolutely, absolutely. I wholeheartedly, I wanted to emphasize that none of this could have happened in a 1 year time frame without 4 master students working with us and without faculty members doing the scientific aspect of it. And that's a that's why I emphasize it 4 or 5 times that the collaboration is the name of the game. Of course, we are in a company, you know how strict they are with proprietary stuff, but we can always find a way because the metrics for academia is publishing. Students have to graduate. So we have found a sweet spot where neither of which is affected, I totally would, I'm glad you brought up that point again. So, and I just wanted to add with respect to the tools, really, it's impossible for everybody to have everything. Again, in India, we have such fabulous tools available at several institutions. So, especially academic institution to institution, it's very, very competitive prices. And especially for students, everybody is indulgent for even free. So I strongly, advise you to look around and please reach out to me for any help for metallurgical characterization. I'll be happy to direct you to the right tool. Of course, the tool has to work at that given time. I'll be very happy to connect you.
Yes, exactly. And she talked about so many things, and some of the simple sentences he made could be a lecture by itself, like design for manufacturing. Just one simple statement, and this is the lecture by itself. There are a lot of stuff like that. Now, however, before I take too much time, let me ask one simple question. Now it is Deepaji for yourself, just for my curiosity. Obviously, in typically user additive manufacturing, there are different techniques. Whatever technique you use, mostly you use, I'm assuming, some sort of powders. I'm also assuming they are in this range of 20 to 50 micron. before I put my question, let me make sure I'm on the right track. Is it true or false?
Yeah, it's true. For powder
Okay.
bed fusion, it's of that range. Yeah.
That is my question now. And it's my question. I'm thinking about it for some time. It's my mental experiment I'm doing for a long time. The question is that if we suddenly, by miracle, you want to increase the particle size from 20 micron to 100 micron, the whole process will change. Okay? It may or may not even work. And go to the other extreme, instead of 20 micron, by magically, if we can use 1 or 2 micron particles, again, the process will whole ballgame will change. A lot of the problems we are thinking or seeing in terms of 20, 30 micron, 10 to 30 micron particle size, and trying to melting them and try to coalesce them and try to take out the heat treatment, bonding, and joining those things and taking care of the metallurgical issues like thermal stress, etc., will probably go a lot if we magically can do it. Now, obviously, there's a question of cost-benefit analysis. My question to you is relatively simple. Have you looked into it at all and think about using particle size single-digit micron and see what does it do in terms of your product quality, product life, product reliability? Yes,
Yeah,
but
sure.
I know it's a research question. I don't expect anything a lot, but I'm just
No,
asking.
it's a constant endeavor to continue to change particle size distribution. So it's a very good question. Thanks for that. I just wanted to, so in the direct energy deposition process, we use actually upwards of 50 to about 150 microns, because there, you have a coaxial nozzle. It is a cousin of cladding, except that nozzles come either wires or powders they use. In fact, Dr. Jyoti Majumdar, I don't know if he's from your college, Professor Jyoti Majumdar from University of Michigan. Unfortunately, he passed away last year, but
Deepaji,
he's a pioneer.
he's our distinguished alumni from 1972 batch of metallurgy.
Yes. He's a fantastic. He's one of the pioneers, truly, and a guru for all of us in this field. Of course, personally, he's a close friend, so I thought I should mention his name. He was a pioneer in working on this particular research aspect, like long before, way ahead of time, actually, 20 years ago, to change the particle size distribution. In the direct energy deposition technique, they do use larger particle sizes, which is why in the chart that I put in terms of the attributes of different manufacturing techniques, that naturally has a greater surface roughness and post-processing. Now, coming to the smaller particle size, what happens is powders, the smaller they are, it becomes difficult to handle, they clog up. Smaller particles have a larger surface area. So they tend to clog up in the mechanical machine as the recoater blades move like this layer by layer process. So very large particle size with this, more than 50 microns, 60 microns. What happens when you have a laser? You need to have a higher power laser than the fiber laser we use, which is up to 1 kilowatt, in order to have an overlap of the melt zone. Otherwise, there'll be a lack of fusion. So all these are very valid points, and I think a lot of people are doing modeling as well as experimental work to optimize the Gaussian distribution or non-Gaussian distribution of powder particle size distribution for efficiency of the productivity also. So that, right now it is seen as a low volume process, a slightly low process in terms of productivity, the laser powder bed fusion. With all these ideas that you are discussing right now in terms of powder size, particle size distribution, people are working all over the world by OEMs as well as equipment manufacturers, powder manufacturers like Sandvik, Oerlikon, many people to increase the productivity. I hope it answers your question.
Thank you. I understand the direction. You are right. Nothing is easy. There is always a trade-off. Okay. I'm opening up for other people because I don't want to take out the whole thing. Okay. Students, you should ask a lot of questions about additive manufacturing. The biggest
Namaste, Deepaji. I'm still a student. My name is Biman. I'm an 81 metallurgy graduate. I consider myself a lifelong learner like anyone else.
True.
Quick question, what is the scale of the single crystal sizes for the turbine blades that you could manufacture with this 3D or additive manufacturing processes?
Actually, yeah, thanks for the question. Maybe I misrepresented. This is a actually investment cast blade only that I showed you, because it's a blade that is actually from an engine. I don't think, to my knowledge, I don't think people have yet, either in GE or Pratt or Rolls-Royce, at least to my knowledge, or even in the universities, they've not been able to make single crystals more than a few millimeters. And that too, I think Professor Suman Das, I don't know if he's in Euro distinguished alumnus also. He used to be at Georgia Tech, and then a couple of people in Europe, and of course all the OEMs, which is closely guarded secret, have not been able to make single crystals epitaxially more than a few millimeters. So that is still at a research level only, because there is a breakdown when you epitaxially make not more than a tip of the blade. Full blade, to my knowledge, people have not made actually yet with additive, because the heat transfer is so complex that in order to maintain single crystal, typically we seed it and then we grow, right, in investment casting. It's very difficult because of the rapid solidification in additive manufacturing. Directionally solidified, there is little more success. People have made, OEMs have made through more from direct energy deposition than laser powder bed fusion. But to my knowledge, again, nothing is qualified and in the engine yet. I may not be up to date because I don't know the secrets of some of our competitors, but I'm pretty sure if they've made it, it'll be out there for all the media to know. Because it'll be an engineering marvel actually.
Thank you, thank you. And I know this is not a topic of your discussion, but you briefly mentioned about the advantages of the thermal barrier coating and how we could actually take the materials beyond their melting point or close to the melting point. Could you please just add a couple of sentences for our students, especially the Abdullah and other materials background faculty members, that how it is possible?
Yeah, sure. Actually, it has been used since the last 30 or more years, since actually the first thermal barrier coating dates 1956, I think, in the military engine. So thermal barrier coatings are typically, the typical workhorse is yttria stabilized zirconia, zirconia with 8 weight % yttria. That is the magic number of thermal structural integrity with thermal stability. It has a thermal conductivity in the bulk sintered part of 2.2 watt per meter per Kelvin, whereas the nickel based or the anything that is protecting it is typically about 60 to 70 watt per Kelvin. And for the sake of students, if it was a class, I'm sure I'd have asked you what is the thermal conductivity of the. So the best thermal conductor of copper is about 400 watt per meter per Kelvin. I just wanted to give you a perspective of the numbers to keep in mind. So yttria stabilized zirconia is used as the thermal sprayed coating. And the closest I can think of, I'm sure a lot of universities have it. I don't know if you have it, but definitely CGCRI, a few other, closer. I'm just talking IIT Kharagpur. They all have some thermal spray systems near you. Maybe even you have, I don't know. But so these are put by thermal spray right now because of the plasma 200 kilowatt gun that is used to melt the ceramic powders and then coat them as an overlay coating out here. And because of they are ceramics and very brittle, we are not able to put more than 1 millimeter. Even 1 millimeter is an overkill. 1 millimeter itself is able to achieve enough protection that they don't for whatever engine cycle, they are able to protect the hardware, the metal beneath it, so that the metal can last, the blade can last for several years, whereas the thermal spray coating itself is sacrificial and has to be stripped and recoated after every so many cycles. Yeah. Does that bring you a perspective?
Yeah, thank you very, very much. Thanks a lot.
So YSZ is the standard material for TVC?
Yes, YSZ is a well-known material. Of course, a lot of research all over the world for the last 20-30 years. We also have gadolinium zirconate I think it is qualified for aero engine applications almost 15 years ago. You see, Santa Barbara is people, a lot of people have worked on Professor Carlos Levy, Professor Tony Evans, Professor Teresa Pollock. Many people have worked on this, names you would recognize, so I'm telling you. Gadolinium zirconate is used by all the OEMs, including Pratt & Whitney. It has a bulk thermal conductivity of 1.1 watt per meter per Kelvin. So at least for the students, guess how many years, how many PhDs, how many masters, how many millions and billions of dollars all over the world, both East and West, was used to get from 2.2 to 1.1. I would say there are at least 20 years of work has gone into that to get by 1 watt per meter per Kelvin a structurally a material which is having good structural integrity. In India, of course, ARCI in Hyderabad is doing a lot of work on it, amongst many others. Many other people are also working, but thermal spray community is relatively a small community.
And to what extent Pratt & Whitney is employing additive manufacturing component-wise?
I showed
if
you.
you
I mean,
can-
in India, we are only a small R&D center here, but globally, I showed you in the first or the second slide very extensively. Yeah. And they're also doing all the advanced technology research. I think Professor Sarkar was asked, he was mentioning, we're also working a lot into multi-materials now, not just metals and ceramics, embedded materials. It has gone into a completely different level now in terms of advanced technologies. Globally, we're also working on some of them with specific universities in India, into taking it into something which is 10 years from now, at least university professors are only interested in very far-reaching things. And we at the R&D Center bridge that with our application. So, I would say I'm at the best of both worlds.
Yeah.
In terms of learning for ourselves,
Actually, the holy grail of additive manufacturing is that if you can draw something, I can build something. Okay,
Yeah.
and
That's
that
what they
is,
say.
yeah, this is a challenge for conventional manufacturing. The other real advantage of additive manufacturing is, as Deepa was talking about, this data transfer. One of the advantage of is that if there's a big thing, if we can start making production parts, okay, there are a lot of challenges, then life will be totally changed. In that case, what will happen is that what I've been talking for some time, that the whole world is enslaved under the Chinese government as a basically manufacturing hub of the world. That will be go away right away. And now we can do the manufacture anywhere. We can do it in Vietnam, we can do it in India, we can do it anywhere you are, New Zealand, it doesn't matter. Because all I have to do talk about it, data, transfer the data, and is a additive manufacturing is a technology driven tool. So what will happen is that we can always do manufacture one thing anywhere you want, and if there's an issue in that particular manufacturing place, we can go to the next place, which is maybe 100, 500 meters or miles from there. So that's another huge deal. So this is the so-called distributed manufacturing we are talking about. That's another thing. So I think the additive manufacturing has its own place already established among the researchers and scientists. But what we are looking for from this present day students and technologists that to make it as commonplace as conventional manufacturing. Then the whole manufacturing syndrome or dependence on Chinese will go up. India will become one more place to go for. That's my hope, at least.
Actually, Dr. Das and the organizers, can I take leave now? I don't mind coming, later and giving another talk on thermal spray coatings. I think somebody has a question. Raise the hand. If you don't mind, can I answer that? And can I leave? I'm really sorry because I have a patient at home to take care of. So I
you have to
need
close
to
it.
go give my mother some dinner. I'm really
No, no.
sorry. I have to cut short this.
Then
meeting.
Dr. Das,
Yeah,
let
yeah,
me take
sure.
this
I
opportunity.
think somebody had a question, Dr. Mukhopadhyay or someone, Anirudh. If you want, I can answer that. And
it's okay. I don't want to open another question and then take your 5 minutes or so time. We'll
sorry.
catch up.
No,
some
please,
other time.
yeah,
Thank you
please,
so much. No
Dr.
problem.
Sudeep
No problem.
No, no.
has Professor, they all have my email ID. I'll be very happy to connect with you anytime tomorrow, even in a Zoom call.
Yeah.
But,
We look for more opportunities in conferences.
Sorry, I
and
have to
seminars.
leave. That's why I said we'll start at 6:30. So
Okay.
Let me just briefly express our thanks on behalf of the Centenary Celebration Committee as well as on behalf of the department. Let me thank you for giving this nice lecture. Right, we hope to meet again on online or offline, any whatever platform we might have in some seminar or conferences. Let me also take this opportunity to thank our today's chair, Dr. Devdulal Das, for nicely handling this session, running the session. Let's all release or speak today's speaker. We have a certificate for her. We will be sending it. The digital copy will be sending, and the hard copy along with a memento we'll try to send through post to her address. So thank you, ma'am. Thank you very
so
much.
Yeah, thanks for having me, and sorry
thank you,
to
Dr.
interrupt this interesting session.
Please take care of your patient at home.
Yeah, thank you so much. Bye-bye.
Thank you, ma'am.